So hi everybody, I'm Caleb. My group mates are Benito and Faisal, and we'll be presenting on using convolutional neural networks to do classification of brain tumors. So like I said, our problem statement is motivated by the fact that over 700,000 Americans are living with brain cancer in the US today, and over 19,000 will die this year. Accurate classification of brain tumors is essential for the diagnosis and treatment of them, but it's very difficult. As you can see in these images, tumors of the same type can appear differently, and tumors of different types can look like each other, making it hard to tell them apart. Our task, though, is to try and develop a machine learning model that can accurately classify the different types of brain tumors from fMRI image data. A little bit about our raw data. We had over 3,000 images, but luckily there were no missing values in here. There were 233 patients that contributed images, meaning that each patient contributed a number of images to the data set. Here are 3 example images that show what a class 1, class 2, and class 3 tumor image might look like. On to our EDA. Some things we learned from our EDA. The first thing we looked at were the number of tumor images per tumor type, and we saw that some classes, specifically glioma, have far more samples than other smaller classes like meningioma. This motivates us using upsampling to balance classes later during model training. We also looked at example tumor images from given patients, and we saw that even within patients, scans can vary in the amount they're zoomed in, their rotation, and kind of what side of the image the tumor is on. This motivates us to use careful data augmentation to try and not corrupt data, but still add some variance to it. And then lastly, we looked at the number of unique patients that contributed images to each class, and we saw that this number was different for each class. This motivates 2 considerations when we split the data. We want to split on patient IDs to make sure that no patient has images in more than one of the train, validation, and test set to avoid data leakage. But we also must stratify the label when splitting to ensure that there's at least 1 patient for each label in each set.
In terms of modeling, our approach is to begin with a simple logistic regression and gradually add more complexity to our modeling approach. We choose the logistic regression because of its simplicity, and that makes it the best choice for a reference model. And then we fit the basic CNN regression on the original dataset. Because class imbalance was a problem in our data set, and also we had limited data, we proceed to do upsampling on the training data set to balance the class, and then we do the data augmentation. We fit again the basic CNN, and we proceed after that to do transfer learning using state-of-the-art models such as ResNet and also MobileNet. And finally, as part of our extension requirement, we use, convolutional XGBoost that we saw from a paper have been able to achieve, improve accuracy on classification tasks. So the conv XGB, in terms of architecture, it consists of a stack of convolutional layers, and that has XGBoost as the final layer. The idea is to reduce the number of parameters in order to deal with a problem of, overfitting that we kept having during the training process.
All right, so on to our results and conclusions. So these are different test accuracies for the different models that we had. And one thing we noticed is that the transfer learning models and the conv-XGB model worked the best. So we had the highest accuracies of 0.92, 0.91, and 0.91. And one thing we noticed was that the 3 largest increases in accuracy can be accounted by the fact that we use CNNs instead of using basic regression approaches, which definitely improved our model accuracy. We applied a lot of data augmentation and class balancing to the training data. And we also used transfer learning with the state-of-the-art models such as ResNet and MobileNet. Now, this is a graph of our F1 score per model per tumor type. And once again, we noticed that the transfer learning models and the conv-XGB model worked the best. Across all the models, the pituitary tumors were classified the best. And this could indicate that meningioma and glioma are more similar to each other than the pituitary tumors. And also, once again, we noticed that the class balancing and data augmentation greatly improved the F1 scores for the low performing classes as well. So some of our limitations are that we only use 3,064 grayscale images from 233 patients. And that, to be honest, is a very small number of images to do such a large, expensive task. And also we noticed that overfitting was a major problem. So a couple of areas of improvement we can look into are we can use multiple regression regularization techniques, like different techniques that we can do to further reduce the overfitting. We can collect more data and train the models on that data. And we can also look at other state-of-the-art models. And these are sources. So thank you very much for listening to our presentation and hope you enjoyed our project. Thank you.